So, just like with the Bernoulli random variables, binomial random variables also have nice, quick and easy little formulas for their mean and variance. So if you know that you are dealing with a binomial random variable, then you know, and you know its parameters, then you know what the mean and variance are. So real quick, so if x is distributed binomial in p, then its mean is just n times p, and the variance is just n times p times 1 minus p. Now, I don't know about this, but this, I think, makes a lot of sense. You might want to stop and think about that for a minute. Why should the expected value be n times p? We'll come back to that later. But let's prove this right now. Okay, so let's see. The expected value of x, I just start with the definition there. It says to take this weighted average of all the possible values that x could take on. Okay, I'll let k be my dummy variable there, and I'm going to multiply by the probability weights there. What's my probability mass function for a binomial? It's n choose k times p to the k times 1 minus p to the n minus k. Right? Again, so this part is my probability weight. Probability weight, or probability mass function. Okay, tells me where the values are sort of concentrated on the real line, where they're more likely, and where some of them are more likely than others. So remember, this tells you the number of ways to choose the k positions out of the n to put your successes, your so-called successes, and then I'm raising your success chance here to that number of successes, and this is your chance of failure for any one trial, and you're raising that to the number of failures, right? If k is the number of successes, then n minus k must be the number of failures. Okay, so you can see that it's just the weighted average of the possible values, right? I'm summing up all the things it could take, all the values it could take on against the probabilities that that's what it is. Okay, so I'm lucky because I know what the answer is. I know that all this stuff is supposed to simplify to be NP. So the first thing I'm going to think about doing is trying to factor out an NP. But actually, before I do that, I might notice that, hey, you know what? If k is 0 in this summation, the first term here is 0, right? Because 0 times all this stuff is 0. So I don't have to start with 0. I could start with 1 and go to n, right? Okay, and I'll say times k, and then maybe I'll remember what the definition of n choose k is. Tutorial, and I got a p to the k times 1 minus p to the n minus k. All right. Now at this point, I'm going to remember that my answer is n times p. So if you already know what the answer is, or even if you don't, but you have a good idea what it might be, then go ahead and factor that answer out, and then show the rest of the stuff is equal to 1. That's a good little trick for you. So I'll pull an n times p out. I'll be left with k goes from 1 to n. Got a k in here. Let's see what's in this fraction here. This is now raised to the k minus 1. This is 1 minus p to the n minus k. This will be n minus 1, I think, factorial. And then actually I can cancel that k with the k that's in the bottom here. Have k minus 1 factorial times n minus k factorial, right? Now, this looks an awful lot like n minus 1 choose k minus 1, and in fact, it really is n minus 1 choose k minus 1, because look at this. Isn't this the same thing as n minus 1 minus k minus 1? It is. This just this and here, all that is, right? Okay, so in fact, yeah, this is just going to be np times the sum, k goes from 1 to n, of n minus 1 choose k minus 1 times p to the k minus 1 times 1 minus p to the n minus k. All right. And now, can we say that that all this stuff is 1? All this stuff? Yeah, actually we can. But before we just jump right to that, I'm going to play a little trick here. This is a common thing when you're dealing with sums, is to change the dummy variable there, change the index to be something more convenient. What I might do is I might come over here and say, let's let k prime be equal to k minus 1, and so that means that k equals k prime plus 1. Okay, so now I can rewrite this summation in terms of k prime. So I'll say k prime goes from 0, okay, up to n minus 1. See that? Could check, see, if k prime is 0, my first term here is n minus 1, choose 0. If I go up to here, if k equals 1, then my first term here is n minus 1, choose 1 minus 1. This will be a 0, right? So our first terms line up. That's good. All right, so then what does that make this? That means this is now, instead of p to the k minus 1, it's p to the k prime. Right? Then I'll have times 1 minus p to the n minus k prime minus 1. Okay? Now, look at this. Okay, they have this dummy variable going from 0 to n minus 1. Okay, I've got n minus 1, choose k prime. I could change my n minus 1s if I like to be a m for math. Okay? Here's an n minus 1 here too, right? I got it. So this is all m minus k prime. Guess what? By the binomial theorem, this is 1 by the binomial theorem, and we're done. So the mean is just n times p.